amazingly enough, we have we have four hands-on groups that are going to be presenting. The amazing part about this is 2 of them are remote and they're from India, and it's the middle of the night there. So talk about dedication. So yeah, so I'm as soon as, oh, we do the side by side on that thing, on that one. We don't do it on here. Okay, we're just making sure we're set up. Okay. Okay, so if we can have the folks from Project 4, Remote Team 1, to turn your camera on and start talking, then it should pick up your it should pick up your thing, your video. And I can move your slides from here. Can he unmute? So who is it?
Okay, so am I audible?
Good. Go for it.
Okay, so yeah, I guess this is kind of like my first presentation. So yeah, everyone, wish me luck. My name is Avinash Salvaneshwar Nediyartha, which is quite a long name. And for all the attendees out there, we will be working on the group project for the 4th hands-on session, which will be the WASP-77A emission spectrum retrieval project. So can we go to the next slide, please? Okay, so for those who are actually there and do not know what the aim of the project is, it is basically to find, to find the retrieval of the atmospheric properties of the WASP-77AB. It is to basically reproduce the result of another research paper written by August, and it is to compare the metallicity and the carbon to oxygen in the atmosphere, which was also reported in that same paper. We will also be carrying out an on-off analysis, and the metallicity is equal to 1, which is going to be 10 times its solar. And we will also be comparing the retrieved pressure to temperature profile with the one that is reported in the research paper as well. So next slide. So just so before we actually start, we have a disclaimer. So the thing is, we are all just normal students. We don't know any better, and there's a good chance that we might actually say something terribly wrong, or we might come to the wrong conclusions. So we are all here to learn and grow together. So if you guys have any doubts, or if you guys think that we said something wrong, you guys can all correct us towards the end of the presentation, where we can actually openly discuss about it, because believe me, we have more doubts than you do at this point. Okay, and we have been working on the code for quite a long time now, because there's a mix up in the time zones and everything. So it wasn't easy, and yeah, I hope you all understand, and we can actually get into it now. So this whole presentation is going to be put up into 3 different subsections. So we are going to start with the preliminary observations and comparison. So for those who do not know out there, I hope some of them do not, so that this starting area does make a little bit of sense. So we will be, this whole project is based on the WASP-77AB. It was found in 2012. It's a hot Jupiter with an equilibrium temperature of 1700 Kelvin. It has 1.4 days of orbital period, 1.6 times the mass of Jupiter, blah, 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 all the things which you can read there. And the main reason why this planet is so interesting is because, the main thing is that, it has been found to be depleted in metals when compared to its solar, both based on high resolution spectroscopy in both ground-based and space-based observations. Next slide. So yeah, our observations are taken from the James Webb Space Telescope. Surprise! And we use the near-infrared spectrograph using the G395 grading. And the whole eclipse data was actually just loaded directly from the research paper. So we did not use Eureka or any other pipeline here. Next slide. So a qualitative difference in approach. So according to the paper, the paper in the paper, August had done nested sampling algorithm using 1,000 live points, with a resolution of 20,000 opacity files for their molecular opacity, whereas in ours we had to use 50 live points because we had to run it on a single core processor. We do not have huge 24 cores processors to work with, and even the retrievals were actually used in August's paper. A different pipeline has been used, whereas we used Petit Rat Trans. 3 models were used for the temperature pressure profile, whereas we had used only the Gilead temperature pressure profile. Yeah, so for the analysis, I would like, Arkaprabha to carry on with the rest.
Yeah, thank you, Avinash. Hello, I'm Arkaprabha Datta from ISA Kolkata, and I'm going to present and try my best to describe the code that leads to the result. So there are roughly 8 segments of the code. I'm skipping all the installation and importing parts there in the notebook. Now, first we should talk about the data preparations. Avinash already talked about the data collection through JWST. Data retrieval part is not much complicated either. The only task at our hand was to bin it down to a manageable amount of data. The binning process for both part of the spectra is shown here in the diagram. I'm not going to show the code because the only change we have to make was the path, and which also depends on the system. Next slide, please. So the next part would be assigning fixed and free parameters. Now we want to create an atmospheric model. So we start with some parameters. We select some fixed parameters as temperature and radius of the star, along with radius and mass of the planet, as they are very accurately calculated. And for free parameters, we add infrared opacity, gamma parameter, internal temperature, and equilibrium temperature. For the atmosphere, as Avinash mentioned, it's a depleted planet. We also add free parameters for chemical models, the Fe by H and carbon and oxygen ratio also. And for the opacity, the last bottom corner, we consider the collision-induced opacity due to hydrogen and helium. We do not add the Rayleigh scattering of the hydrogen and helium here since it's negligible in the mid-infrared. Next slide. So the next and most important part of the code was to come up with the forward model. So as it is very big and a little bit of tweaking can actually modify the code. So I used this hands-on session 4 WASP-39b forward model and tweaked some part of it. Here are the, we copy the get stellar spectrum function from the introductory exercise to calculate the eclipse depth. Next slide, please. So in the forward model, we actually did 5 changes in the from the WASP-39b code. First one was obviously the definition. Then we used a Gilead global model instead of isothermal model in WASP-39. Then we added the chemical parameters. Next slide. And the last 2 things were in WASP-39. We used to calculate transmission. Here we try to calculate the flux from the star, and from that we get the stellar spectrum, and from that we define the spectrum model. Next slide. This is where we try to describe the loading and plotting of the data. So we load the data from NIR spec G3958 spectrum for both blue and red part. The code was completely given there, and for the best fit spectrum also, there was a suggested section, and we just followed that one. Next slide. Now, for the code for retrieval part and running the retrieval, it's not complicated, and there are some changes we did. We removed previous emissions before running a new one, and I added that mostly because this is one part which was extremely frustrating, because we did some mistake earlier, and it was it took a long time to fix that. Next slide. Now, once again, the final fitting and corner plot, the code was given. The fitting, from the fitting, we actually get a very good result. In the result section, Avinash will explain that. And corner plots, I think for a few of them, the posterior plots that we got are a little flat, but for quite a few of them, using the same code that were given, we got pretty Gaussian plots. Next slide. And finally, we get a little sneak peek to the PT profile. I wanted to give it beforehand once, because there's one thing that's happening. We are actually using a toy model here pretty much. Avinash explained before that there are a lot of differences from the original paper. So, which is the reason, although we are supposed to ideally get pressure versus temperature inversely proportional, but in reality, outside of the contribution peak, we should not get so much constrained curve. But inside of the contribution peak, we get a pretty good curve. So I think the data is actually works in some sense. Thank you. I think Avinash will take over.
Okay, thanks, you did a good job. So now we are actually getting to the results of the whole thing, the most awaited segment. So we first have our multi-nest outputs, which are, I have to say, they were very tedious, because every single time when we were trying to run them, it used to crash, and then we had to run everything again from the beginning, since we were all using Colab, and yeah, it was a huge pain. But yeah, when you actually look at these outputs, you can see that the gamma, H2O, carbon monoxide, carbon dioxide, they are actually not constrained well. You can see that the posteriors are actually not Gaussian, they are actually flat posteriors. We do not really know why this is the case. Maybe it's because we used equilibrium chemistry, but then, we are not sure. Okay, now that is like one of our biggest doubts over here. So yeah, you can actually see the statistical fit parameters for, our metallicity and the carbon to, oxygen ratio. Yeah, you can go to the next slide. And yes, the star of the show, the best fit plot. The best fit model, as you all know, represents the theoretical atmospheric parameters and the spectral features that are, observed within the observed data. So it is the main model that provides the closet match to the actual observations. So, you can see that you can actually see it based on the best fit and the ones that are observed. And you can also see that the residuals are they're actually fine. They actually fit pretty well. And in the next slide, we had done a comparison at a glance. So the measured metallicity value is actually very close to our reference value. The slight difference of like 0.02 is actually relatively small, and it does fall within the uncertainties of the measurements. The measured carbon to oxygen ratio is also kind of close. Again, there is a difference between, how relatively small the measurement uncertainties are. But this indicates that, the carbon to oxygen ratio of the object's atmosphere is also kind of in like a good agreement with the reference value. Overall, based on the comparisons, it does seem like both the metallicity and the carbon to oxygen ratio are kind of consistent with August's paper. Next slide. So the spectrum at different metallicity. So when the metallicity is actually reduced to 0.1 times solar, it means, the star has very fewer heavy elements, being iron. And, as a result, the absorption lines of the metals in the star spectrum will be, much weaker and less pronounced. And actually, this is how WASP 77AB actually behaves. And as you can see, when it is equal to -1, when the metallicity is equal to -1, it is actually kind of similar to the original plot, since what we got was, minus 0.97 something. So since it's actually very close, you can see it doesn't make much of a difference. Whereas the moment you change the metallicity to 0, which is going to be very much similar to our sun, the spectrum of the star will actually exhibit absorption lines which are almost the same characteristic of a G-type star. And when the metallicity is further increased to 1, which is like 10 times its solar, it means that, there is significantly higher abundance of heavy elements. So I am assuming that, these dips could be for the molecules like, carbon dioxide or methane or H2O. And we can actually see, if we go to the next slide, that actually, when we do the on-off analysis, that, carbon dioxide has an absorption band in the infrared, and one of its significant absorption band occurs around 4.3 microns. So we can see that when we actually completely leave out the carbon dioxide, the dip, kind of goes away. And like, this is what I'm assuming is happening. So I think that it does correspond to the vibrational rotational band of carbon dioxide, and that's why it's causing a dip in the spectrum. And since we kind of remove that, the dip no longer is there. So in the next slide, okay. So now this is going to be, a temperature pressure profile. Arkaprova already kind of said quite a lot about it, but I personally think that within the, contribution regions, it is actually agreeing pretty well. Like, I do think that there is a pretty strong correlation inside the contribution regions. So this kind of suggests that our model used in the analysis does capture similar temperature pressure relationships in those regions. I think that's pretty much it. In the next slide, if we go, you can see our team that we worked on right now. There were originally 8 of us, but then because of all the time zone issues, it was very difficult for all of us to actually, make time for all these things. And yeah, to be honest, I just came from school today, and I was just sitting in front of the computer for like, I don't know, 12 to 14 hours on stretch, both me, Arkaprua, and basically everyone else on the team. So yeah, I really would like to, congratulate everyone from the team for, making something like this possible. And I really thank everyone at Nexi for actually making this possible for us. And that's it.
Okay, so we have Paul here who can give you some feedback, I guess. So go ahead.
Yeah, thanks so much. You did a really good job. I'm actually very impressed. I made some comments, so I don't forget. And I also like your slides, really, they're beautiful. So yeah, I think, very little comments. I think it looks actually very good. I think a few things I noticed that you mentioned, for example, you compared the resolution, we should look there, when you compared the resolution between the two models, PRT is like 100 and Brune Auguste used like 20,000. It's a different method for treating the opacities. So I think they're basically doing the same thing ultimately, but there was no way that you could have known. I think I have to apologize. I think I should have been a bit more careful that, you had this problem when there's something wrong in the forward model, and then you run the retrieval and doesn't delete the old files, that you'll always run into a bug when you try to rerun. So I'll make that clear for the future. So sorry about this. And
This is fine.
What else? Right. And one more thing. When you said like, oh, it's only, well, inside the contribution function, where the contribution function is high, the Petit profiles agree very well. That's as expected, and that's good. And above and below, you still get very tight constraints because the pressure temperature profile, you set the parameters of it in the contribution region very tightly, and they can also predict what's going on above and below the contribution function, but it's actually good that you were suspicious because there's actually no information there. It's really the parameterization that makes this. So this was also very well noticed. Yeah, so I'm actually amazed. So very, very well done. Thank you.
Thank you.
Oh, thanks a lot for your feedback. It really does help. Are we allowed to ask questions? Oh, okay. Fine.
I think actually we need to move on. We don't have time for more questions.
Oh,
but
oh yeah.
yeah,
Okay, thank
yeah,
you.
but you could put them in. If people have questions, put them in Slack, and the Slack will remain open, so everybody can communicate after the workshop.
Oh, yeah.
Okay. Thank you very much.
Oh yeah, thank you.
Thanks.
Yeah, thank you.
And I hope you can get some sleep.
Oh yeah, definitely. I am lacking quite a lot.
Yeah, I'm sure. Well, thank
It's
you.
actually 3:53 in India.
Yeah.
Yep.
Bye.
That shows a lot of dedication. All right. So our next group is Project 3 Remote Team 2. So we have another remote team. I can run your slides for you if that works. Okay.
Yes.
Okay. I think we're good. Yeah, that's right. Okay, go ahead and start.
Hello, ma'am. Hello, everyone. Thank you for handling slides for us. I'm Abhijit, presenting before you about our project on fitting models to data. And accept my apologies in advance for mistakes, which I definitely going to make, I think. As I am newcomer to this fascinating field of exoplanet exploration, and I feel privileged to be part of this project. All the knowledge that I draw and gain through this participation of summer school, it's my only knowledge for this project onwards. Can we have the next slide? Yeah, our project basically is to use grid fitting tools of Picasso to analyze reduced spectra from different instruments for exoplanet WAPS 39b. The goal is to determine the best fit cloud-free and cloudy parameters. Parameters being metallicity, C2O ratio, internal heat, and heat redistribution. And cloudy parameters being metallicity, C2O ratio, intrinsic heat, and heat redistribution, and log KZZ. For each of these grid fitting, we have the following reduced spectrums as NI, RI, SS, SOSS spectrum. Second being NIR spec G395H spectrum. Third being NIR as spec prism spectrum, and fourth being NIR CAM F322W2 spectrum. To start the project, first we need to load all the data sets for the indicated instrument, and we try to plot the transmission spectra using just plotted tool of Picasso. Now, what is a transmission spectrum? As this whole project is based on transmission spectrum, I wish to elaborate a little on it, although I believe everyone here knows that pretty well. So, basically, a transition spectra refers to the graphical representation of the amount of light or electromagnetic radiation that passes through a sample, which could be a planet in our case, as a function of its wavelength or frequency. Like in exoplanet exploration, it is a technique in which a telescope is used to study starlight passing through an exoplanet's atmosphere, revealing its composition and other parameters. Like here, as you can see, we plot the spectrum for NRI ISS SOSS instrument, which has a wavelength range from 0.6 to 2.8 micron. Thereafter, thereafter we plot a spectrum for NIR spec G39 5H, instrument, which has a wavelength range of 2.4 to 5.2 micron. And can we have the next slide, please? Like, can we have the next slide, please?
I did change it. Can you see it? It's on the
Yeah,
major
yeah.
spec prism.
Yes, sorry.
Okay.
The spectrum for next we have the spectrum for NRI spec prism instrument, which has a wavelength range of 0.6 to 5.2 micron, and its transit depth ranges from 0.0200 to 0.0230. And thereafter we have our final spectrum for NIR CAM F322W2 instrument, which has a wavelength range of 2.4 to 4.2 micron, and transit depth ranges from 0.0200 to 0.0217. Next slide. Our parameter grid for cloud-free atmospheric model consisted of parameter as internal internal temperature with values 100 Kelvin, 200 Kelvin, and 300 Kelvin. Heat redistribution as 0.2 and 0.5. Metallicity ratios has values as 0.1, 0.316, 1.0, 3.162, 10.0, 31.623, 50.119, and 100.0. Carbon to oxygen ratios as 0.029, 0.452, 458, 0.687, 0.916. And if we sum up all the possible models that we can generate from this parameter grid, it will sum up to 192 models. And for cloudy grids, we have parameters as internal temperature with same values as cloud-free grid, heat radius, heat redistribution as same values as cloud-free grids. And then we have metallicity ratios, and then we have carbon to oxygen ratio, and then we have log KZ, and we also have forward spectral energy distribution as FSCD. The total models for cloudy atmosphere, it is sum up to 3840. Next slide. In this project, we actually have to answer 6 questions. First being, what are the best fit cloud-free parameters for each of the 4 instruments? Are they similar or different? Are there cases where second question being, are there cases where different data reduction result in different best fit cloud parameters? Our third question is, does including clouds affect the best fit model? Next question is, how does the best fit cloudy model change for each instrument? Are some instruments more affected by clouds than others? And our next question is, are there cases where different data reduction result in different best fit cloudy parameter? And our final question is, do any best fit parameters seem meaningfully constrained by the dataset? Are any physical parameter better constrained than others? So we try to answer this if I address our first question, using data analysis and model fitting by tools provided by the Picasso. The link for collab you can find at the last of the slide. So there you can find all the calculations and codes and all the analysis. To address the first question, as we observe from this table, that the parameter values for metallicity ratios is kind of different for NIRI, SS, SOS, and for all other instrument it is same. And next, for the carbon to oxygen ratio, we observe that NIRI, SS SOS and NIR spec G395 has same values, but NIR spec Prism and NRI CAM F322 W2 have different values. Same goes for intrinsic internal heat. And when we observe the heat redistribution, we find that NRI CAM F322 W2 instrument has different values, but other instrument remain same. So like here we can conclude that yes, like obviously these are the best parameters for each instrument, and and here we can conclude that like parameter values like they are a little bit different for different instruments. So that's our conclusion to this question. And our second question, to address our second question, like, are there cases where different data reduction result in different best fit cloud like free parameters? So for this, we analyze NIRI CAM F322W2 through Han Solo reduction datasets and Eureka reduction datasets. Here we also observe that metallicity, like metallicity being the same, remains the same, but carbon to oxygen ratio, internal heat and heat redistribution like kind of deviated a little. Like if you can observe that carbon to oxygen ratio is 0.687 for Han Solo and 0.229 for Eureka. Same goes for like for internal internal heat, it is 200 Kelvin for Han Solo and 100 Kelvin for Eureka. Heat redistribution being 0.4 for Han Solo and 0.5 for Eureka. So, like, can we have our next question? So like the final, like our third question is, does including cloud affect our best fit or like best fit model? So yes, as we observe from the graph of the NIRI specs prism reduction spectrum, like that, if you can observe it closely, that blue line represent best fit with cloud, and the orange line represent best fit with without cloud. So you can find that cloud seems pretty cloud seems fit pretty well, whether cloud free is quite kind of like uh, low fit or something. So like these bumps, if you observe these bumps, they like for cloud and cloud free atmosphere, it has a huge difference. I like kind of saying that in terms of best fitting. So from like this graph, we clearly conclude that clouds affect the best fit model. Like, can we have and also if you can observe the chi-square ratio also answers like same in terms of that. We have chi-square ratio kind of 10.25 for cloud free environment and 6.22 for with like cloudy like atmosphere. So yes, it does including cloud does affect the best fit model. Like, can we have the next slide? Here are two another plot for NRI spec G395 and NRI CAM F322 W2, and here also we observe the same thing. So like from here on, my group mate Divya led the presentation, and I will join you later.
Okay, so am I audible? Abhijit, can you please confirm?
Yeah, you are audible, Divya.
Okay. So hi everyone, I am Divya, a final year master's student from India again. And so here we are generating the grids for using Picasso 1D model. We are generating the grids of WASP 39b. So it's, as he mentioned, it's a gas giant, and it orbits a G-type star and has a orbital period of around 4 days. So since he has already answered the first three questions, I'll go about with fourth and the next questions. So in the fourth question, we have how does the best fit cloudy model change for each of the instruments? And we have the data from 4 of the instruments of JWST, and we are trying to vary the parameters like CBIO ratio, metallicity, intrinsic temperature, heat redistribution factor, to check which of the values of the varied parameter would fit the observed spectra using the Picasso 1D model. So yeah, so here we have for NIRIS, we have metallicity of 3.162, and for for NIRSPEC, PRISM and NIRSPEC G3958, and for NIRIS, we all of three have the metallicity of 3.162, same metallicity. But for NIRCam, we are seeing a very huge difference, which is 100. Now for CBIO ratio, the CBIO ratio seems to be, it is same for NIRIS and NIRCam, but it is slightly different for NIRSPEC. Intrinsic temperature, it's almost the same for NIRIS, NIRSPEC and NIRCam, but for NIRSPEC PRISM, it is higher, which is 300. And the heat redistribution factor is almost the same for all of them. And log KZZ, which is the eddy diffusion coefficient, it is also pretty much similar for all four of the instruments. Next slide, please. Yeah. So we see, so in the next question we have, are there cases where the different data reductions would result in different best fit cloudy parameters? So for this, we have taken cloudy exoplanet, and we have done the data reductions, the reduction pipelines of Han Solo and Eureka. Using these two pipelines of the data from these two pipelines, we constrained the metallicity, CBIO, intrinsic, heat redistribution, and log KZZ. The values are as here. So moving from Han Solo to Eureka, the metallicity changes really way too much. The CBIO ratio is pretty constant, the intrinsic also is constant, heat redistribution is almost the same, and the KZZ slightly varies. Next slide, please. Yes, so these are the posterior plots, and here we see that which of the, so out of all the best fit parameters, which one would be meaningfully constrained by the data set. And here we have taken for, one is for Eureka and one is for Han Solo. And we see that the intrinsic temperature does not, the probability values do not vary much for the best fit parameters, 100, 200, and 300. But a log metallicity is quite fluctuating in both the cases, and CBIO ratio is also fluctuating. So maybe we can say that A intrinsic is the best fit. It is fitting the best among all the parameters present over here. Yeah, next slide, please. Yes. So these are the contribution plots for each of the molecules. So this is done. So initially, when we have the model, we have all the molecules present. Now, to plot the contribution, we would try to reduce one molecule one by one. So we can know at what wavelength there is a peak. So we can say that in the spectrum at that wavelength, if there is a peak, then the molecule corresponds to that. So as you can see, in no methane case, there is a peak just below 4.5 microns. And also for no water case, there is a peak below 4.5 microns, almost very similar. That means in the transmission spectra, just below 4.5, within 4 to 4.5, the peak could correspond to methane and water. And CO2 does not show that sharp peak. And yeah, for including all the molecules, the spectra is also present. The same thing also has been done for rest of the instruments, and the different peaks can be observed here. Because of the time constraints, we had to limit the slides to this much. And then next slide, please. Yeah, so this is our team. Abhijit, me, Jitendra and Rajesh. So at the last moment, we were the only 4 people who could work on it, and others, since it is India and it's almost early morning now, so people are sleeping. Next slide, please.
Thank you.
Yeah. Yeah, that's
yes.
all. And we have also provided a QR code in the next slide if people would want to have a look at our collab.
Oh,
Thank you so
okay.
much.
Cool. Let me get this out of the way. Okay. And so we have Natasha here who can give you some quick feedback.
Yes. Awesome job. It was very cool to see you walk through every single one of those questions and look across different instruments and also across different data reductions. A few let's see, two points of feedback. One thing that's very confusing is SED, we do commonly refer to as stellar energy distribution, but with FSED, it's actually sedimentation and it controls the strength of the cloud deck. And then the only other thing is, so the is it possible to go back to? I just wanted to go back to this real quick. So this was really cool to see too. And your conclusions from this was that the internal temperature was maybe the one that was most constrained. But one thing, there are two interesting things I think from this plot. One is you can see that in the cloud-free cases, the probability for some cases of being at higher metallicity is higher. And so cloud-free cases tend to want to be at higher metallicity, whereas when you stick in the clouds, you can see that the bucket of probabilities at that 100 times higher solution kind of decreases just ever so slightly. So, you know, you're not really getting meaningful constraints, but and then here for C to O, you see kind of equal probabilities here, meaning maybe you couldn't constrain these parameters, but a big drop here. So maybe you could exclude those solutions.
Oh, okay. So C by O greater than 0.8 can be excluded, right?
Yeah, that was really confusing, and we also didn't go over it. So I was really surprised, and it was very cool to see these up here. And then everything else was really awesome. You picked up that NearCam was the least sensitive to metallicity, and all the other instruments agreed, which was really cool. And it was really interesting to see that the data reductions were swapping out different C to O's, but the metallicities were consistent, which is sort of what you would what you might expect. So yes, that is great, awesome work.
Thank you so
Thank
much.
you, ma'am.
Okay.
Thank you for feedback. Like, and as for conclusion, I would like to thank all my group mates, and as we join together work on this project, it is very wonderful and fun experience. I would also like to thank the organizing team and all the participants and friends that I made here. You all are awesome and wonderful, and participating here is such a blessing for me. Thank you.
Thank you. All right, let's see. All right, thank you. And thank you for staying awake. We really appreciate it. All
Thank
right,
you, ma'am.
now let's see if I can. All right, so next, I believe we have one person from Project 3 in-person team 1. Yes. Oh, that's not you though. Yep. Okay, hang on. Sorry. Let's see. There it is. All right, now I have to figure out how to share because we just lost Ellen. Where did this
Can you hear me? Oh, yeah. Yep.
For like 5 minutes But I told you they really do all the work. I'm not kidding.
Before I start, just I'm surprising because I don't know if I'm gonna represent that with my part of my crew because I thought that they live in. So thank you for the support. And hold raise their hand who is in my group that is still here right now. Yeah, yeah. Okay, good enough. Yeah, no big deal. Don't worry. Yeah. So yes, this is the disclaimer because we choose first to not present that because we only want to learn about how to use Picasso. But I changed my mind and the group support me this week, this morning, 10:30, I think so. So this presentation is like not well done. Sorry about it. I'm Laura and
Max, Peter.
so we're gonna do today is show you what you can do by yesterday using Picasso. Disclaimer, I'm working with atmospheric scape. I never touch on those transit spectra stuff. So please don't be bad with me. I don't know Max or Peter, but I have work in different things. I think so too, isn't? Yeah. So yeah. So the workwear issues was the same one that you just presented, that just have the presentation right now, is the WASP 39b. This planet is a hot Jupiter around a sun-like star. So here's the comparison between Earth and Jupiter also. Because I didn't have expected that you're gonna present with me, I just took the part of the work that I did. That is with Toby. Toby also did this part. Hi, Toby. I don't know if you see me. And we choose the near spec to with the Prisma mode to work into. So, oh, thank you. You're so nice. So here are the characteristics of the planet. So he's have a really short day, like 4 days. He's a hot Jupiter because it's too close from the star. The mass of the radius of the planet is about 1.2 the radius of the Jupiter in our system. So can you go for another one, please? So okay, let's go. How you go for this and this using Picasso Eureka for this. Precessional ice spectra. So yeah, so this is how I understand it. At least I don't know if you want to talk, just the microphone, go ahead. I can do, we can do that all the time, all the day. So here's the spectra. So since I'm not a spectra person at all, and not observation now, I work with modeling. So I try to find out in Google each lines of absorption are in this range. So go above, please. Yeah, this is what I found. So you have water here, sulfur dioxide. I also have to looking for the names because I'm physicist, I'm not chemistry. And we have CO2. We have magnesium silicate, this one. And we have this feature that I have no idea what it is. I have this one also, and CO2 again, like a huge one of CO2. Let me see my. I have disclaimers here all to ask to teaching you what I'm trying to say. So yeah, I have this feature that I think it's a high lag scattering. I think so. Not sure. And go to the another one, please. And yeah. Thank you. So for the posteriors, or you can see that you cannot constrain the temperature, sorry, from the inside the planet. So it's okay. You can move on. And you can go for the next one, please. Okay, so we have 2 types of modeling. With no clouds, with cloudy. So when you have no clouds, the posteriors show us that you have like for explain what you're seeing, you have like a huge metallicity on this planet, like 100 times the solar metallicity in our solar system. But if you add clouds, you have a lower metallicity because you can blame the clouds, and it's just 10 times the solar. And another one, please. So in another slide, you can see that no clouds and clouds again, like red and blue. And this, what I understand is the refractory elements. So it's the ratio between carbon and oxygen. So when you have no clouds, you have to add more refractory elements to explain that, because you don't know, we always have to blame the clouds. I think that was Kevin that told us that before. So I'm doing that right now. And if you put clouds, you have you can explain better by in this part of the posteriors how is the results, because you move the distribution for here. So maybe the answer is here, you know. Okay. Next one, thank you. So I know that it's not a terrestrial planet, but I am a terrestrial planet person. So I always try to see other planets, like I can understand that and understand a lot of Earth because I like meteorology. So here's what should be the tropopause, like 0.1 bar. And this is the mixing ratio pressure graphic of this planet. So what I understand that happens here, and those points here, and here, this bumps in the point could be forming some cloud of those elements, that is CO2, water, methane, and we have a little bit of silicate oxide, I think so in English. And you have also phosphine, is that it? So yeah, could be considered like a false positive. I don't know. Yeah, because it's in a gas giant planet. But I mean, you have it's a positive but a false because it's a gas giant planet. So this is how I understand for the presentations. So here again we have TP, the temperature profile of the atmosphere. I just put the tropopause for everyone just to guide the eye. So this is how the temperature changes when you go up in the atmosphere. So yep, go another one. And this is the opacity profile for another metallicities in the atmosphere. So here again, that our tropopause, and maybe, I don't know, this is decreasing here because here's the tropopause where it's forming the cloud of this two here and here gases in the atmosphere, because we have no sodium sulfur, that is the blue one in the atmosphere, and we have prescovita, I don't know how can I say it, magnesium silicium oxide. I'm so sorry for it. I try my best. And we have M and N, I don't remember, but it's something with sulfur again. And maybe we are forming clouds in this of that in the planet. So we have clouds of methane, water, CO2. We have false positive to phosphine. You have these two maybe cloud formations and different parts of the structure of the atmosphere. Remember that you have this pressure, so you're going up in the atmosphere. Here you're going down. Okay, so next one, please. Oh, that's it. Okay, so thank you for my wonderful crew, please. And thank you for receiving me here. It's my first time in person. I'm so happy. And I just came to this workshop to learn Picasso, and I finally got there. So yeah, and thank you all for all the volunteers that helped me. So, and this Christy, I don't know where she is. Yeah, there. Yeah, thank you. And thank you, Natasha, for the help in the lunchtime. And thank you for my supervisor, Evgeny Shkonik, because it's the second Congress meeting in less than 6 months of first year of postdoc. She pays to me. So thank you so much for your attention. And that's it. And please tell me all the things that is wrong. I'm totally open.
Okay, nothing was wrong. You all did awesome. Your energy is awesome. I think it really livened up the everyone is just so stoked on WAS 39 right now. This cracked me up because you got sulfur dioxide here and here, but this guy is sulfur dioxide right here. And I think what led you astray is in this. You made this really nice contribution. Oh wait, no, where was it? Oh, maybe you just showed me offline and didn't put it in here. But SO2 wasn't in the opacity file that I gave the students to create from 1 to 5 microns didn't include SO2, so only the 3 to 5 micron did. So I think that also made it difficult when you were doing the analysis to figure out what that feature was and whether or not it was or not SO2. And then the only other thing is these are the cloud profiles of your best fitting model, which was awesome to see. The enstatite is forming, that's the MGSIO3 is forming all the way down here. And then, yeah, like you said, the MNS sort of picks up later. But if you look at like the optical depth of 1 profile, optical depth of 1 is like here. So in this profile, you probably are, the way to interpret this is to go, okay, optical depth of 1 is about here. Move that over, that's at around like, 0.1 bars. So in this transit spectrum where the contributions are probably coming from about a millibar, you're seeing a little bit of contribution to the cloud, but maybe not so much. But anyways, this was also all awesome to see.
Thank you so much for your attention. So yeah.
And I before I have to take off for a flight, they don't know this, but Taylor, Aaron, and Kevin are going to give, since they're experts on WAS 39, are going to give feedback to the last group.
Thank you so much. Good job. Ellen's back, so everything will work now. Can I have the last group? So project 3, in-person team 2. Come on down, please. Why don't you introduce yourselves while Ellen's getting this up?
Hi, everyone. This is going to be for the 3rd group project. We're the 2nd group. This is just a testament to what you can do in 24 hours. But just to notice up front, we will probably not be as energetic as the last group. But given that you just saw 2 groups that just did this presentation, we'll skip a lot of the intro stuff, and we'll just get straight to figures probably. So I think this is it. So this guy is gone. Who wants to give this one? Yeah, you did the other. So
okay, this does work. So yeah, so if you want to be seen by the camera, come over here.
We perform the model fitting for the different instrument with in JWST. Okay. And so first instrument is NIRCam instrument reduced with different software, T-shirts, this one and Eureka and Han Solo, and different data set result in different result slide. And left file shows the best fit
SED of model fitting. And basically, H2O is necessary for fitting the data. And this is I did the model fitting for data used in the Nature paper. And the result is basically similar with previous one. And this is a bunch of number of best fit parameters. And there is a take-home message. Yeah, that's all. Okay, next.
All right, so I'm going to be talking about the data that we analyze. This data is from the near spec fixed slit grading mode, which is to differentiate it from using the micro shutter assembly. And so just for a little bit of context, so this was done using this particular aperture, which is this little square one in the sort of bottom right of this image. And it was done using this grading, in case that means anything to you. Now, to be clear, the instrument used in this mode nominally can cover anything from, I think, 0.6 to 5.3 microns. And nominally, it has a resolution of about 2700. But the way that these authors use the instrument, the particular aperture and grading they use, and the way they binned the spectra, they covered this sort of 3 to 5 micron region and had a spectral resolution of about 600. And there's also a detector gap that corresponds to the region between 3.7 and 3.8 microns that you are going to see right now. So this is the reduced spectrum that was taken from this instrument, superimposed with 2 Picasso models, one that does not include clouds and one that does. The one that does include clouds is in blue, and you can see just sort of visually, as well as from this chi-square metric, that this cloudy model seems to be a better fit, which is not entirely surprising, as I think we've learned throughout this week. And if we go on a little more, we can see the posterior distributions for 3 of the variables that we fit for a small subset of them. And we can see that there are some variables that this data is pretty agnostic to, such as the internal temperature, which in a way makes sense considering that this is a hot Jupiter. So its radiative properties are going to be more or less entirely determined by the radiation that is coming from the star and incident on it. And it's also fairly agnostic to metallicity here on the bottom, even though it disfavors things that approach this is the carbon to oxygen ratio, and it disfavors things close to and presumably over 1. There is a bit of a preference for higher metallicities, and as you can see for our best fit parameters over here, it sort of converged on a metallicity of, I believe that is 10 times solar for this particular reduction. And then finally, we can see the molecule by molecule contributions here. And the really obvious feature at 4.4 or so microns corresponds to carbon dioxide. So that's pretty unambiguous. And the contributions of water here at sort of either end of the covered wavelength range seem to pretty strongly indicate its presence as well. There doesn't seem to be any significant amount of methane. However, it makes no difference really whether or not you include it. Now, this is all for a particular reduction. You can see it's the exotic Jedi reduction, which is a fantastic name. But the authors of this paper did 11 separate reductions. So, and they also included a weighted average of all of those reductions. So when we look at that data, it doesn't change a huge amount for most things. You can see that the chi-square for the cloudy model has improved, and the chi-square for the cloudless model has actually gotten worse. Doesn't make a huge visual difference though. Nor does it make a crazy difference with the posteriors. The best fit parameters do change a little bit for this internal temperature. It goes from 300 to 200. And the metallicity goes from 10 times solar, it goes down by about half a dex. And the individual chemical contributions themselves about the same. Carbon dioxide right here, water on either of these ends, no significant methane contribution.
Okay, for nearest SOSS data, yeah, as you can see here, the cloudy model with the blue line looks better. Also, it gives the smaller chi-square value, but for both best fit model, cloudy and cloud-free model, these are the best model parameters presented here. But cloudy model, as I told you, it's a little bit better. And then here is the also some probabilities of the models. And then overall, cloudy model looks better. And then for cloud-free model, it prefers high metallicity, as you can see here, the red line. So 100 times large metallicity. And then C2O ratio less than 0.8 might be, it must be it is likely be less than 0.8. And then for cloudy model, so I feel like there's no constraint on the internal temperature, as you can see the similar probability for all three temperatures, and not strong prefers between the three C2O ratios, like looks similar to me. And then also similar metallicity for the blue bars. So I feel like there's no preference model with this data, at least. And then for final, the best fit model here. So I feel like the H2O must exist, as you can see the presented as the orange line, no H2O model versus the other model gives you very big difference. So it means that H2O must exist, but not sure for CH4 and CO2 with just this data. Yeah.
All right, and then I'll end it off. So I did the near spec prism reductions. One of my favorite parts of this exercise has just been looking at all the different reduction names. So for near spec, we have Eureka, Firefly, Tiberius, and T-shirt. Whoever came up with T-shirt needs another grant, I think, because that's a great name. So what I wanted to do is just highlight the differences between all of these. We're back in the 3 to like 5.5 micrometer range. For these four, I really appreciated Firefly. It just has the greatest density of points. And as you can probably expect, for all of these, we found that the cloudy cases had the best reduced chi-squared. And in all of these reductions, we do end up pulling out some version of that SO2 feature that we have all come to love. With our probability models, as you can probably expect, our internal temperatures, we still don't have an idea of what that is. Most of these, it does seem to, for these four, most of these still tend to point to a higher metallicity ratio than the stellar standard. And once again, they all tend to have a everything. It's going to be a C to O ratio of less than 0.8. Yep. And you can see a little bit of the subtleties here. You'll notice for like Eureka and Firefly, you can't even tell the difference between all of the molecules combined and leaving out methane. So methane is probably not a significant feature for this planet. But you can see if we leave out CO2 in all of these plots, there is something significant. It's very obviously significant. And at the edges again, if you leave out water, your spectrum changes again. So in summary, it's cloudy, there's SO2, and there's definitely CO2 and water and methane to be determined. And that's it. Thank you.
Okay, so who wants to give the feedback? Great. Taylor.
Well,
Can you
yeah, we're venturing into very dangerous territory as we get a person who makes these spectra to help interpret the spectra. So anyone in the audience, feel free to weigh in, Kevin or Aaron or whatever. In general, I think you summarized things well. Definitely CO2, definitely water. Some things matter a little bit between reductions. Yeah, it makes sense that you're like low C to O because you see water, and so even in instruments like NIRISS where you're not seeing any carbon atoms, you're seeing water, and high C to O kills off water. So that's where that's kind of coming from. I don't know. Did anyone else want to weigh in? I think generally it was well done and consistent across the board, which is good.
Yeah, no comments on sort of anything wrong or anything like that. I just wanted to say it's super impressive that you did this in 24 hours. You should be really proud of yourselves because this is crazy. And that goes for all of the other groups today. Like I'm kind of blown away a little bit of how much everyone managed to do. So yeah, pats on the back for everyone, I think.